Okay, as we continue the second part of the lesson about our sampling distributions. So, the first part of the class, we took a sample of just four scores. But reality is, I have a lot more than four students. I have a total of 54 students in AP Stats. So, what if I wanted to take a sample of five students and from this group of 54? What would happen? So, what I'm going to do is take a sample of five scores from my 54 students. And I'm going to do it four times. So here are the values I got. And again, you see the scores here. And think about this. Could I ever get a number repeated in this one sample of five students? Yes, I could, if I had more than one student who scored that. So for instance, I don't think I actually did get any with repeats in here when I did it, but if I had had two students who scored a 74, it is possible I could have both 74s in this single sample because they represent two different student scores. And for each sample that I have, I calculated the mean, which we represent with X bar because it is a sample statistic. So again, a statistic comes from a sample, and if it's a mean, I'm going to use X bar to represent it. Okay, and then I'm going to create a dot plot. So here is the dot plot of our sampling distribution. So this is the sampling distribution of X bar. So every dot on here represents the mean from a sample of five students. Okay, there are 30 samples total on here. They range from a 68 up to, 92, 94 as my mean of the sample. And again, I've tried to show you that each one of these is a sample mean. So it's from our sample of five, what does that mean? Okay, what does each dot represent? I just answered that. It is a random sample of five students and the mean score calculated. What do we think the true average is? It looks like it peaks around 82. And when I calculate it from all 54 students, the average was 82.1. So this tells me it's unbiased, that my mean of the sampling distribution equals the population mean, which is represented by mu. And again, that's a good thing. That allows me to use my normal distribution. Sampling distribution, it shows that shows the mean from all possible samples of size 5 from the population. So is this a true sampling distribution? No, it's not, because we did not have all possible combinations or samples where we take 5 from the group of 54 or the population of 54. If I did have every possible combination, I would have 3,162,510. I'm not going to do all those. What if I took a sample from another high school and their mean was 68? Is that convincing evidence that their students did worse than the students at our school? Or is it possible they have the same average? Well, what I'm going to do is come back up to the simulated sampling distribution here, and their mean was 68. So I've drawn this line in, and I'm interested in ones that are smaller than that. So I only have 1 point in there out of these 30 simulations I did. So, is it possible that Rockford has the same average? Yes, but if they had the same average as our school, it would be very unlikely, there was only 1 out of 30, to get a sample mean of 68 or below, which suggests when it's below 5% that the our assumption that they have the same average is not accurate, right? So again, if we get a value or a probability of less than 5%, it's probably something wrong with the assumption. Okay, here is our learning targets for the day. Let me zoom in a little bit here so it's easier to see them. How do we evaluate a claim? First, we assume the claim is true. So just like in that previous one, we assumed that Rockford High School has the same mean that we did. We create a simulated sampling distribution, and then we find the percentage chance of getting the observed result. And that would be, if it was just due to random chance, what is the chance of getting that result that we claimed? So what was the chance of getting a result of 68%? Well, we only had it happen once out of 30 times, so very unlikely. If the claim is true, here's my sampling distribution. I'm looking at the percentage of dots. So in this case, I wanted what's the percentage of getting higher than some observed result? There was only 2 out of some number here. If that percentage was less than 5%, we have convincing evidence against our claim or against our assumption. If the probability of it happening, the percentage is greater than 5%, however, we do not have convincing evidence against the claim. So we have to basically assume the claim was true. And we've got now another check your understanding. Please pause this and do the problems yourself. See where the gaps are in your knowledge or where you get stuck, and then come back and listen to my explanations. So hit pause. Okay, let's go over this. This is going back to our very first unit, population parameter, sample, and statistic. Population is everything. So our population are all the pennies in this jar. The sample are the 50 pennies that we drew out. The parameter, so what is the proportion of pennies that were, pre-1982? So our proportion was 0.132, and that's from the population. So we use the symbol P. The statistics, this comes from the sample. There were 11 out of 50 that were pre-1982 pennies, which is a 0.22. And again, for a statistic that is a proportion, we use p hat to represent it. So that tells people that's from a sample, not from the population. Does she have some evidence that more than 13.2% of her pennies are pre-1982? And again, some. We're not asking about convincing yet, but some evidence. Sure, she has some evidence because in her sample, she had 22%, which were pre-1982. So that's greater than 13.2, so it's some evidence. 2 explanations for this. First could be that the percentage in the container is only 13.2, and she got lucky in her sample. That the sample she picked of 50 pennies was just a lucky sample and had more than the norm. Or the percentage in the container really is greater than 13.2%. Okay, so that's what we're going to want to test. We use technology to simulate 100 simple random samples of size 50 from a population of pennies in which 13.2% are pre-1982. The dot shows p hat, and again, p hat are the proportion from each sample of 50. So each dot represents a sample of 50 pennies and what proportion of them were pre-1982. And there was a total of 100 samples done. So that's what the dot represents. And assuming that 13.2% of the pennies are pre-1982, is it surprising to randomly select 50 pennies in which p hat is 22% or greater? So we're going to look at this simulation with 100 simple random samples, find 22. So looks like it's about right there. And then say, is it surprising? Yes, because only 4 of the samples had 22% or greater. So 4 out of 100 is only 4%. This only happened 4% of the time by a simple random sample. And then based on our answers, is there convincing evidence that more than 13.2% of the pennies in her jar are pre-1982? Yes, there is convincing evidence because the chance of this happening by itself is so low. So assuming that her container only had 13.2% copper pennies, it is unlikely to get a sample of 50 with 22% or greater. And again, remember, we use that 5% as our cutoff. If we had had higher than 5%, then we would have said, okay, we would believe that claim. But we did not have something higher than 5%. Okay, good luck on the homework.